Are you aware that with CockroachDB, nodes can go down, nodes can come up, the thing can seamlessly move across the topology and adapt to an ever changing landscape, and it does that without you having to be directly involved. We're going to talk about all that, but first, I want to bring in my good buddy here, Felipe. How's it going?
Hey Greg, how you doing? Barely made it. All these connections, man.
Connectivity issues are
Yes,
the plague of our modern era, I think.
yes.
So we're going to cover some really cool stuff. We're going to get into some of these basics about CockroachDB. How does CockroachDB do what it does under the hood? We're going to dig into some of that. But I wanted to share some fun facts. This is something I learned about, a gem of a fact I learned just a few weeks ago. Cockroach is 10 years old this year.
Yeah.
Um, I went and did some digging, and you know what I found? I went and found this. I went and found the Git commits. This is the very first commit at the top. This is the first four commits of CockroachDB, and they're by our fearless leader Spencer Kimball. Now, I would like to have dragged him onto the show to pick his brain on that, but many of our learned colleagues right now are in Austin, Texas, for our beginning of the year revenue kickoff, or beginning of our fiscal year revenue sales kickoff. It's Nerdvana over there. I wish I could be there, but I found this, the initial code for a huge shop building a enterprise cloud scale database with ACID compliance is what do you know? The first code was written by our CEO. I did some digging because I looked at the date. The date on here says February 5th, 2014, and suddenly okay, the math started clicking in my head. So wait a minute, that's not 10, that's 11 years. So I went and tracked down. I had to know the answer to this before I got on the air here to share this. So I found a bigger nugget of knowledge here. This is when the domain for CockroachLabs.com was registered on January 23rd, 2015. So 11 months after that commit, or yeah, about 11 months and like a week after that first commit we just saw was created, a company was thus born. So the 10-year celebration, I didn't bring special effects to play to throw confetti and all that, was 10 years ago, January 23rd, 2015 is when Cockroach Labs became a thing. And since then, there's been ups and downs. I wasn't there for all of that, but since I've gotten in there, it's been a huzzah and it's taken off, and it's been really exciting. You're sort of the new man on the scene, Felipe. So I don't know what your gut reaction is to having been here for about a month now.
A month. Yes, yes, yes. I joined what was January the 7th. Yeah, so happy to join to this amazing team, and of course the education team. So kind of getting ready for starting doing deliveries, right? So
That's
pretty
right.
excited.
So cool. So here's what I promised. Let's get to the main subject here. Our main topic is I want to talk about uh, some of the fundamentals. Now, there's a lot of fundamentals. We can't cover all of them, but I wanted to kind of hone in on one specific one. Let's see if this is the fun game of I need to pick the right tab here to share. Let's see. Is it, yeah, it's this one. Okay. So what we have here is um, this is a slideshow I'm bringing up here, and we're going to bounce around. We're going to talk about this, but I want to talk about one of the core features that CockroachDB is built upon. And this is called ranges, replicas, and leaseholders. And that sounds like three $5 words all bundled up and thrown at you at once. Um, what I want to talk about, I'm going to contrast with sort of where things were, and what kind of problems do we have out there today? What are the problems that we're having, and what was CockroachDB built to tackle, and how does it do it? Um, in legacy databases, at least when you go back to I entered this industry back in like 1997. Back when we were using you know rocks and sticks and stuff to build software. We had databases back then. Databases, like relational databases, like 50 years old. Um, but we've seen in the past 25 years, 30 years, a huge growth in like e-commerce sites. And instead of building a system that serves the customers in your city, you're serving customers from around the globe. So people start with a bigger customer base, you need a bigger database, right? So you keep growing and you start to run into you need bigger and bigger systems, and you run into scalability issues. So you run into the fact that you just have to serve all these people. They have to be able to read data, make updates, make inserts, this kind of thing. And then the side effect of that is, they say, what is it? More money, more problems. Well, a bigger database server, a bigger maintenance budget you need to maintain that server. And then as new technology gets built, you're having to integrate with new stuff. So instead of just having, here's my here's my database server, and here's the web server that sits on top of it serving clients, in this region. Like maybe I've built a system and it's in San Francisco and all my customers are in the Bay Area, that kind of thing. You now reach a point where I've got this server, but I have clients coming in from around the globe. And they're now using newer and newer tech stacks, and you're having to deal with that. So there's a scalability issue at play here. Now, in the past, it was, well, I don't know. If we've got more customers, we've got more revenue, we can afford a bigger box. And so it was always build a bigger box, build a bigger box. Well, there's a certain point at which there are no bigger boxes. Now, AWS was sort of a trailblazer in that it unleashed the ability to buy way bigger boxes, in a sense, by going to the cloud. We were able to grab stuff and do that. And so it extended the lifetime of get a bigger box a bit further. But we reached a point where even with the deepest pockets, you run out of room. You run out of runway of being able to do this. So now let's delve into some of the ways that we dealt with this. We realized you can't just build a bigger box to replace the smaller box. So instead, you start thinking, I'll just get 3 boxes. Okay, I'll chain the 3 boxes together to make a virtual single database on top of that. So in a sense, that from the application's perspective, it looks like one big box, if you will, one big database at the top, but it's going to spread the data across my 3 machines that I have in the cluster, okay? So in a sense, we call this partitioning, where we need to divvy up the data. I'm going to put some of the data on machine A, some on B, and some on C, and this has traditionally been referred to as sharding. We're chopping up the data. We're going to shard the data, okay? And this got us a little bit further. That helped out a little bit. But we started to run into issues with this as well. And what are some of the challenges? Well, first of all, you need to come up with a strategy. How am I going to split the data up? I need to split it up to store it on the servers where they're going to store the data. But then when somebody wants to read the data, I need to merge the shards back to fetch them out. So there's an element of splitting and merging, okay? And then what else do I run into that? Well, there's issues about where am I going to place the data? What's the structure of the sharding? I need to think of that in advance, because I may be holding 100,000 rows in my hands today that maybe I have a good idea how to split those up, but what happens when I get the next 800,000 rows of data? Does my placement strategy work for that? Are there issues I can't see that are coming up ahead? And what if I started with 3 servers, but I need to expand to 10? What do I do in those scenarios? And so we talked, that's some data placement of having to divvy stuff up, but then I run into failure circumstances. I need to cope with those, because one of the things is with a big box, a big box solution that we were just looking at earlier here, if you have a big server, there's a sense in which, okay, at some point I'm going to have an issue with the server and it goes down. So traditionally, we've built high availability solutions by having another equal and identical big server sitting right next to it, usually with an ultra high speed network cable connected to it. So in a sense, a backup server can take over, like that with no problem. But when I've moved into this sharding solution, what now? Like what if, in this case, what if server A goes down? unless I've got a strategy to handle this shard, this portion of the data, if a piece of the data goes down, then my data has lost all consistency. So from a sense, that aggregate diagram that we just saw, it takes your database down. So, we have issues about availability. And what it does is it exposes you to the fact that each shard of your database solution is now become a single point of failure. So in this diagram, I have 3 single points of failure. And, if you go crunch the numbers, maybe the chance of failure is 1%. Well, when you multiply that, it doesn't become 3%. The math works against you in this context. Now that you have 3 points of failure that can happen to you. So some of the things we need to do is we need to increase the availability. So how are we going to do that? So our first solution here is let's replicate the data. Now this diagram, there's a lot of boxes on here, so it may be hard to spot. But let's focus on shard A, which is what we're sort of looking at a minute ago. Earlier we were looking at shard A that was on server A. So down here now we can see we still have shard A, shard B, and shard C, but now there's also 2 replicas of each shard. So we have 3 shards in total and 3 copies. That gives us 9 total copies. So the idea is we realize, okay, to have high availability, we need to replicate this across multiple servers. This comes with its own problem. So at first this says, okay, this helps us beat the problem of single point of failure. So to beat single point of failure, we need replicas. Okay, that's pretty straightforward. But what are some of the challenges with this sort of naive replication? The challenge we now struggle with is consistency. Because we can have it where we have 2 different clients. Maybe each of these, imagine servers A, B, and C are spread in San Francisco, New York, and London. And for best performance, you have all the clients find the nearest copy, the nearest replica to talk to read from. Okay. And so, the West Coast one is accessing shard C replica and trying to do an update on row 1, on customer ID 1 in this case. But somebody else is trying to access the exact same row, and they're accessing a different replica. In this case, you could call it the original, but basically shard C, and they're in London. So you have an issue where one user wants to update that customer to Jamie, and the other one wants to update it to Alfred. You've got to sort that out somehow. And now we're talking about, we're sorting out a problem that's in two different updates happening in 2 different hemispheres of the globe. That is not free. So the question arises, okay, hopefully now what I'm hoping you're catching is what is the problem that we're trying to solve, and so how does CockroachDB handle this problem? I've got my notes up here to make sure I'm not losing track or anything. Okay, so this is what CockroachDB does. Now, step back and imagine we're talking about a relational database. Okay, the big blue or purple disk in the middle represents a database. This is a toy database we have in some of our training material called the Mover database. It's a service that lets you order a car to pick you up and take you somewhere. I'm sure that idea will catch on at some point in the future. People will realize the value of that. So in a relational database, our database is made up of tables. In this case, we're looking at the user table. What CockroachDB does is it takes that table and it splits it up, it breaks it up into small chunks called ranges. Now, a range, if this is the first time you've heard of this with CockroachDB, you can think of it's very similar to a shard, except there's a key difference. In sharding, you're kind of having to manage it, whereas ranges are automatically handled by CockroachDB engine. So you're taking a big table and you're splitting it up into chunks. Now, what this diagram shows below is the top half is the database mapping, sort of our abstract database concept, a logical construct, and the bottom half is the physical construct, where we have three nodes running in three different racks, and in this case, I'm just going to say in three different data centers. We already mentioned rack one, you could imagine, is in San Francisco, rack two is in New York, and rack three is in London. Okay. And in this case, we've taken our database and we've split it up into multiple ranges. The ranges themselves have some characteristics, okay? The ranges are rows of the table and they're in contiguous chunks. Now, there's some exceptions to this that we're not going to talk about today. When you get into multi-region, the range structure changes, but we're not going to talk about that right now because that's a more complex thing. Today we're talking about basics, CockroachDB basics. A given range is a contiguous chunk of rows, in that you're not gonna grab the first row and put it in one range and then grab the second row and put it in a different range. It's more like, let's get the first X rows, then the next Y set of rows goes in the second range, and then the third set of rows goes into the third range. And by default, they break up at the 512 megabyte boundary so that the ranges are small enough that they're easy to replicate.
Greg, if you allow me to do, even before you get into this part.
Sure.
So I want to give like a very quick kind of analogy on this, so we get into more detail on ranges. So guys, imagine like a vast library with a million of books, right? So to keep things organized, the library divides the collection into sections such fiction, nonfiction, history, and so on. So each section contains a range of books with similar topics or genera, right? So practically in CockroachDB, data is organized in the same way. So instead of books, we have rows of data in tables, and instead of library sections, we have ranges. So each range contains a continuous chunk of data from one or more tables. So that I wanted to put my 2 cents on this kind of analogy for ranges.
Now, that's a great example. I like the book thing too, the library thing, because a lot of what I learned in relational databases, I was taught they used the library example, and it really like, oh, okay, that duh. So that's a good descriptor, Felipe. So sharding's basically a precursor to how modern databases are distributing the data like that. And in a sense, sharding is something that's kind of bolted on to older systems. It's an add-on feature, whereas CockroachDB was built from the ground up with this strategy. So what I want you to visualize here, we looked at an earlier I'm going to, not to get you too dizzy, let me flip back to an earlier diagram. We saw this one, okay, where we had essentially three servers, imagine them in three data centers, left like San Francisco, New York, and London, and they have replicas. I want you to look at the same diagram and just transpose it with this one. So each range, we chopped up the table into ranges. Ranges are contiguous chunks of data, contiguous chunks of rows of data, and then we made replicas. So each replica is the same color. Okay. In this case, we have 4 ranges. Now that previous diagram only showed basically what would be 3 shards. Here we have 4 ranges, and there's 3 copies of each range. So that makes for a total of 12 replicas. And you'll notice that they're spread across the servers. Okay. You don't see 2 of the same color on one given server, okay? So CockroachDB replicates the ranges, and the default is to make 3 replicas, the original and 2 more, okay? And these replicas, again, like I just said, they're stored on different nodes. And there's so this is the replication part. So first of all, we need the replication part to have resilience. This way, if the left-hand server goes down, if San Francisco goes down, we know there's a copy of the data in New York and London that we can recover to. Okay, that's the resilience that we're looking for. However, we have to deal with inconsistencies. So in order to do that, each range is assigned what's called a leaseholder, and its job is to coordinate all the rights for that range. So anytime you're doing an update to, say, the purple range, if the row you're trying to update is in the purple range, it's going to find the purple range's leaseholder, which in this case is in the rightmost column in London, okay? So let's elaborate on this a little bit. Let's imagine you're issuing, basically, what's a SQL write? You're doing either an update or an insert. In this case, imagine we're doing an update. This is one of those updates we were doing earlier that we ran into a consistency issue with the shard space solution. So it says when you're doing an update where you say, you specify the customer ID, CockroachDB can figure out where's the leaseholder for that particular row of data. And so that SQL update goes to the leaseholder. So in step 1, the app is going to connect to the leaseholder. The leaseholder is going to take that write update, and then it's going to coordinate with its other 2 replicas. So step 1, the app client goes to the purple range leaseholder to update the contact name to Alfred for customer 1. The leaseholder accepts that update request, and what it does is it puts out sort of an APB to the other replicas on the other servers and say, hey, I need to do an update. The middle replica is the first one to respond, probably because it's closer. The latency is shorter for London to reach New York than to reach San Francisco. It gets it accepts the update, and then it sends an acknowledgement back to the leaseholder. At that point, the leaseholder is able to commit the update. And then eventually, the one in San Francisco is able to sync up to it. Now, we're going to go into this in a little bit more detail. Okay? Now, there's a little bit more here. Now, by default, CockroachDB processes SQL writes in a serial fashion. Now, there's something that's not covered in this portion, but is actually later in some of our other training material, is CockroachDB defaults to serializable isolation. So that means all the updates have to be completed such that it's one after the other. So in a sense, earlier we had a conflict because 2 different clients wanted to both update this customer, one with Alfred and one with Jamie. This is the second update here. Basically, this second update is forced to get in line. So app client 1, while it's doing its update, app client 2 has to wait to update the same row. But once app 1 is done, app 2 client is able to proceed. Now, let me get back to it's fun to bop around here with these multiple things here. Now, what we have is I'm actually digging in using some of our golden training material we actually present to customers, and we actually have hands-on exercises. We're not going to do the exercises today. What we are going to do is I'm going to go on to the next batch of the next bit of content to talk about how does I kind of sloughed over it. How exactly does CockroachDB coordinate doing these updates? I noticed we had 3 replicas for each range. So first of all, let's just recap that. So in this example, we had a table and it was split up into 4 ranges, 4 contiguous ranges. Now the reason they make them contiguous like that is so that it makes it easy to find what you're looking for. If you're looking for customer ID 1, we have basically in the metadata, it can track the range of primary keys in that. So it's like if you're looking for primary key, it's going to be able to figure out, okay, this range of keys, it fits in this one. Okay, where is this located? And in the metadata, it says it's on this node over here. So the client's able to get routed to the leaseholder for that particular range. So the table's split up into ranges, and then every range is replicated. And so in the metadata, it also tracks where the replicas are so it can send out those APBs. So in the next set of slides that we're going to look at, we're going to see how does it coordinate those updates? How does a leaseholder communicate with its replicas? So let's go to that. So one of the things in any situation when you go distributed, you got to think a little bit more because some of our habits, I think as humans we tend to be serial oriented creatures. We're used to I can act on this thing that's right in front of me, and it fills me with a lot of assumptions. And when I go distributed, some of my assumptions can come back to bite me. So let's lay it out here. So CockroachDB builds itself on something called quorum. Okay. In a sense, you need to have what's called majority quorum in order to get for a commit to go through. Well, what that means is, so if we have 3 replicas, a majority of 3 is 2. Okay. Now, let me back up. What this table is showing us is that if we just had one replica, just one copy, we need one copy in order to do a commit. Well, okay, that's nice, but that's what a legacy database does. That's what a monolithic system does, okay? You update the table and you're done. We think about, what if I have 2 replicas? Well, what's a majority in that? It's not 1. 1 is at 50%. 1 is we saw clustering systems that would have 2 nodes, and they would run into split brain phenomena where somehow the 2 replicas couldn't talk to each other, and they would both think that they were the ones in charge, and there was nobody else to tell them that they were wrong. So they built algorithms to handle that. So 2 nodes is not enough to establish a majority quorum. When you get to 3 nodes, now you do, because you can divide in half and round up, or at least make sure you're above 50%. So with 3 nodes, you need 2 nodes to agree to accept a change, to accept a write intent, okay? If you went to 4 replicas, the majority would still be 3, because 2 would put you back into that split brain phenomena. So hopefully you're seeing why it's to our benefit to always have an odd number of replicas. If we go up to a replica count of 5, we need 3 nodes in order to achieve quorum. So Felipe, I'm going to pretend that you're the fun student in the classroom. How many failures can we tolerate if we had 9 replicas?
So we have 9 replicas. So practically it's a factor of the 50. So we can have maybe at least 3, so it's gonna be like maybe 6. It could be, I don't know.
Well, so
if we
have a replica count of 9, this is something it's like okay. If our replica factor is 9, wait a minute, yeah. If the replica factor is 9, that means we need half rounded up, so we need 5 to get quorum. That means we can sustain a failure of 4.
Yes.
So if we lose 4, now there's some more subtle stuff in there. If you have 4 failures in that circumstance, you're now in a risky situation, because if you have one more failure, then you're down. So a recommendation there is to have no more than 3 failures in that situation. That way, if a fourth node if another one goes down, it can up replicate to another one. So that's some fine-tuned stuff there. All right, let's proceed here. Okay. So a quorum is the minimum number of participants required to make a decision. So in this case, now we're back to 3. Let's go back to the simple stuff. The simplest scenario where we actually have some amount of resilience. 3. We need 2. A majority is greater than 50, and it's a common form of quorum. Fun fact, it's not the only version of quorum out there. There's other stuff. I'm sure you can go talk about governments and what they call quorum and stuff. There's in software land, there's other quorum systems like grid quorum. We're not going to go into that, but I just want to let you know it's not the only game in town. And consensus is when a majority of the replicas view the data in the same way. So what CockroachDB does is it achieves consensus by coordinating reads and writes via a leaseholder. So the leaseholder is the term for the leaseholder is coordinating all the changes. So the changes come to the leaseholder. So the leaseholder is the first replica to get updates, okay? So it's going to agree with itself when an update comes through. So when it needs to actually commit something, it's going to contact the other two, and it only needs one more vote to get that. Okay. Now, all this stuff that I'm talking about, this consensus algorithm, is basically built on top of what's known as the Raft consensus protocol. What Raft says, Raft is a protocol, this is a protocol not written by CockroachDB. This is a distributed protocol that's outside of Cockroach Labs, but it's what CockroachDB has picked up and run with. Raft ensures that no data changes are committed until a quorum of replicas is successfully updated. Now, there's actually a website you can go and check if that better. We were going to put it in here, but we actually took it out because there's an animation out you can look up called "The Secret Lives of Data." That's really nice. What we need to do is the Secret Lives of Data. I can go. Yeah, I'm gonna grab this and let me get the right comments. We'll post that out as a message here. There's a link to this great website where you can really see a nice visual on what it looks like. So Raft protocol, basically these three replicas form what's known as a Raft group. Okay, it just means that they're all trying to coordinate for the same set of changes. Okay, and Raft has its own version of lingo. It has what's called a leader, and a follower. And in almost all situations, the leaseholder is the Raft leader. And speaking with one of our more senior people who've been involved in this longer, fundamentally, the leaseholder doesn't have to be the Raft leader, but essentially, within a short time span, the leaseholder and the Raft leader will converge and become one and the same. So replicas for every range form a Raft group. They comprise one leader, and the rest are followers. And CockroachDB ensures that the leaseholder and the Raft leader are the same most of the time. And for the rest of this, let's just assume they are the same. So again, let's relook at that distributed write thing. We kind of saw it in one version earlier, so let's, hey, don't knock repetition. So an update comes to update the customer table. Set contact name equal to Alfred where customer ID equals 1. So first, the app client write request gets routed to the leaseholder. Okay, so CockroachDB has a little bit of code that no matter where you enter the cluster and come into the enterprise, it'll route that app client to the leaseholder for that range. The leaseholder tentatively performs the update locally. Now, I said it does the update, I didn't say it commits the update. What the leaseholder does next, step 2, is it seeks approval to update it from the other replicas. And if you'll notice, there are two different arrows with the number 2, one going in each direction. There's one going to each replica or to each follower. Step 3 is when the replicas send back a signal. Now, if you look on the left, there's a number 3 arrow coming, but it's not quite there. It's got some dots sitting there indicating it's coming. But if you look on the right-hand side, that replica has an arrow 3 that's already made it back. And the moment that the leaseholder receives acknowledgement from one other replica, it proceeds to permanently commit, because now it's gotten 2 out of 3, itself and the replica that responded. And then as the final step, it then notifies the client of the outcome. It's able to tell the client, hey, your commit has gone through. Your update is committed. And what this does is the leaseholder is making sure that it's able to achieve quorum, because then what it's able to do in the background as the app client moves on is it will ensure that any replicas that had not yet gotten the update will eventually catch up and do that. There's some stuff under the hood it's doing that has append log, so that even if you kill and restart a node, it's able to pick up where it left off. So it's got the record in order to affect change. Now, what about read? So we talked about distributed writes. That was kind of a complex scenario. We had to do coordination with all that. So let's look at how reads operate from a CockroachDB perspective in this distributed nature. So it's some kind of select operation, right? Trying to make sure I have my notes up here. So read requests are always routed to the leaseholder. Felipe, can you guess why we always want to route selects to the leaseholder?
Because he's the one that practically manage everything, right? So the
That's right.
leaseholders will respond to the latest read value, right?
It's always got the latest state of what's been committed, so it knows. Well, that's kind of straightforward. There's trade-offs in the way it does it, but fundamentally the client it issues what we call it a read request. It's hey, and the Cockroach Enterprise cluster stuff routes the request to the correct leaseholder, and then the leaseholder is able to give it the per se latest value. Now that ensures that you're getting consistent state of the situation. Okay, that's one of the defining factors of why people want ACID compliant databases. They want data consistency. That's the C in ACID is consistency. Now, so far our presentation here has been kind of strangely enough, this is a simple presentation. Okay. And you're like, wait, simple? This looks really complex. In real enterprises, typically you're not connecting to, I'm going to connect to the New York node. Your app is not geared for that because then you're sitting there having to manage jumping. Instead, you typically have something like a load balancer in your enterprise. Mm-hmm. You can be using the open source HA proxy. We mentioned it here. This does not mean thou shalt use HA proxy. It's just an example. We happen to use it for some of our training material because it's very lightweight and easy to configure. And in fact, CockroachDB has commands. You can feed it the binary that you install. There's a command you can issue that says, "Give me an HA proxy config file for the cluster that we've built." That doesn't mean that's the recommended solution. Instead, use the load balancer of preference. You may be, if you're on AWS, you may be using their LB load balancer. If you're using any other cloud vendor, whatever cloud vendor that you're on, you want to use, the proper load balancer. Now, don't ask me. We need to take that to our solutions architects. If you're running your cluster across multiple clouds, that is something that CockroachDB affords you. Is you can run some of your replicas on one cloud vendor and some replicas on another cloud vendor. And as for where the load balancer is in that, well, you're going to have to make a phone call for that. So, in a sense, load balancers, even a dumb load balancer, a sticky load balancer, whatever kind of load balancer you have, your app clients are talking to it, and it's bouncing you to one node or another in the cluster. A lot of load balancers will use a round robin style approach. Load balancers also typically have some amount of monitoring, not necessarily sophisticated, but their job is to spot, hey, that node seems to be down. Let's not route any more requests to it until maybe we get a ping back from it, that kind of thing. So it helps kind of manage that. So that's more of the resilience and more of the seamless nature of, okay, I'm no longer running on a monolithic database. Now I'm running on a distributed one that's spread across San Francisco, New York, and London. Maybe London's down, so even the clients at London that were talking to the London node recently, they're going to have their traffic rerouted to New York, at least temporarily.
Hey, Greg, now that you mentioned about the load balancer and the HA proxy, this is a command line like a Cockroach chain HA proxy. So that was amazing because I was trying to do my local cluster, and I say, HA proxy, the easiest way, but I didn't remember the whole thing.
Yep.
Now that my cluster was already running, it was very easy just to apply this command, and voila, you have your HA proxy. Now you have your load balancer right there. So that was very
cool. Yeah. It's a really convenient command to get it. And again, I want to emphasize it's not an endorsement per se. It's it's utility. Yes. It's a convenience to help get you going if you want to go that way. But doesn't mean that's the best solution that you ought to necessarily reach for every time. And then here, let's peel the curtain back a little further because we're sharing all the goods today. So your request comes in from the app client. It hits the load balancer. The load balancer is going to, let's just assume it's a dumb round robin load balancer that's able to skip over dead nodes. Okay, the simplest thing I can think of. It's going to pick one. It's going to pick a node to go to. Now in this case, on this diagram, it has picked the one on the left, and it's the node that you connect to in CockroachDB speak is known as the gateway node, and essentially it's the one that you're going to communicate with. This request is going to route through this node, and it's called the gateway node. We have not yet gotten to the point of figuring out what range we're talking to for a given operation, so we're not there yet. The gateway node is whichever CockroachDB node that you hit, and then the gateway node is going to sit there and figure out where to route your request to. All the nodes in CockroachDB are storing. Let me get this. All the nodes in CockroachDB have metadata on where all the ranges are. Okay, or sorry, where all the leaseholders for all the ranges are. Okay, it's able to look at them and say, oh, this operation wants to operate on customer ID 1. Okay, for that table, if you're hitting that table and that one, it's able to look at its local metadata and say, okay, that leaseholder's over in the London data center, so it's going to route the request over there on your behalf. Okay, and it basically directs the request to the leaseholder. And I should add for completion here. It's going to manage the back and forth for this entire request, so it doesn't send you some kind of redirect and then you go over to the other node. Instead, it's going to take the request over to the to the London node on your behalf, and then the results are going to get sent back to the gateway node. So you don't the app client doesn't have to deal with that exchange. So to finish this out, let's look at okay. So the leaseholder is going to process the request. Now we already saw how it does that. The leaseholder is going to do its raft coordination with its other replicas to do the thing. In this case, it's doing a select, so it actually doesn't need to go to the replicas. But if this were an update, that would be where it interacts with the other replicas to form consensus and commit its update. But in this case, it's going to get the select, it's going to get the results it's looking for, and the response goes back to the gateway. And then the gateway is going to hand back the results to the load balancer, and the load balancer relays it all the way back to the client. This is where so now this is the point when in our slides we would then route them into a couple exercises that we have. And you know what? That's the end of our lesson on how to do what is a range. What is a range? What is a leaseholder? And how do we coordinate changes like that? It's kind of a lot to take in the first time. And so if you're like, wait, that was a lot of stuff, you can go back and rewatch this, okay? I like, some people run a show and it's really tilted towards the live stream for the interaction. And so I enjoy those shows, but I want you to be able to come back and watch this again. And you're like, I forgot how those ranges worked or how the replicas work. You can come back and watch this and go through the content and be like, okay, now I get it. So once you kind of get the hang of how CockroachDB works and how it manages those replicas with the leaseholders and the updates, there's a lot of stuff that flows from that quite naturally. For example, well, what if the leaseholder for this range is in London, but I'm in San Francisco? But the data that I want to access, I don't need to see the latest data on this given table. I want to look at the data from 5 minutes ago. Do I have to go all the way to London for that? Spoiler alert, no you don't. You can actually go find a closer replica and get your answer in a more timely fashion. There's other stuff that flows from that, from a resilience perspective, transaction management. It builds on top of this in actually a very nice, positive sense. So I just want you to understand these basics here. So CockroachDB will it takes every table. It also does this to the internal system tables too. It takes every table and it breaks it up into a set of contiguous ranges. and each range is then replicated according to the replica factor. For user tables, the default replication factor is 3. For system tables, the default replication factor is 5. And then it spreads each replica across the enterprise. One of the upshots of all this, a good friend of mine, Deshaun Carter, one of the Spring advocates, he was putting together a presentation that I looked at, and it's really nice because in the olden days when you'd have a giant server in a room with a giant backup server in a room, in that paradigm only one server was ever operational because that's the only way it could coordinate updates and inserts. So in that context, in a vintage monolithic where you have 2 servers but only one is ever active, you're at a 50% utilization. So you're using 50% of your paid for assets. Not the story with CockroachDB. If you've got 3 servers and 3 racks and 3 data centers, the replicas for all the ranges are spread across all of them. All of the servers are fully operational. In fact, there's no single server that's above any of the others. They're all sort of equal. And here's what also happens. You can go add a 4th server, a 5th server, a 6th server, and add it to the cluster after everything has been stood up, after everything's been configured. You can still have the replica factor of 3. I need wider range here. A replica factor of 3, but you're running on 5 servers. It's going to take your database, it's going to chop up the tables into ranges, and it's going to spread them across all 5 nodes, even if you have 3. It just means there's only 3 copies of a given range. So now it becomes a matter of how much resilience do you want? Maybe I want 12 servers with a replica count of 5. Maybe I want, it now becomes a function of what serves your needs and counterbalanced by what's your budget. And you don't have to think about sharding stuff because this is all done automatically for you on your behalf by Cockroach. All right. Now, if you're enjoying this and if you want us to do some more stuff like this, be sure to smash the like button. And I'd say if you want us to do another session like this, maybe on another piece of Cockroach, go ahead and subscribe and ring the bell so you'll be alerted for the next time we have a show coming out. And then leave us a comment about what else you're curious about with regards to Cockroach. We do have a chance if you want to get your mitts on CockroachDB itself and play around with it. We have a free self-paced batch of courses you can sign up for. You can scan the QR code or just go to university.cockroachlabs.com.
And Greg, if you allow me just to do a quick kind of a summary on ranges with a real use case example. Very quickly. So imagine considering an e-commerce application with a table for customer orders. As the number order grows, CockroachDB might split the orders table into multiple ranges based on order IDs or other criteria, right? This allows to the database, first of all, scale, handle a large number of orders efficiently by distributing them across multiple nodes. Already Greg told you about that. Maintain availability. That means that if a node fails, other replicas of the range are still available, right? Ensuring that the application can continue to access and process orders. The other is optimize performance, right? By distributing ranges across different regions, CockroachDB can serve read requests from replicas located closer to the users, reducing latency. Something that we're going to talk about maybe later in a next episode, talking about multi-region. That's amazing topic that we can have. And of course, the key takeaway on this. So range are fundamental concept in CockroachDB architecture, enabling to scale horizontally, maintain high availability, and optimize performance. So by automatically managing ranges, CockroachDB provides a robust and scalable foundation for your application. So practically, you're covered, right? So that's kind of the new distributed sequel of CockroachDB.
All right, perfect. Well, we'll see y'all next time.
This episode is over, but your learning has just begun. Visit CockroachLabs.com to find all kinds of content to expand your knowledge.